Thank you, Reinhard. It's an honor to have the first and the last presentation of this session, actually. So now I have the pleasure to dig into a very specific topic. And I've worked in the topic of reactive power coordination since 10 years. And I will only give a glance of the topic because it's highly complex in the different voltage levels. Just a comment to the previous presentation. Thanks a lot for sharing these nice measurement curves. So in Germany, if I would have this measurement curve, I would just complain against my distribution company that it's not fulfilling power quality requirements. And I think they will find a solution. So we are not dealing now with voltage quality in a specific topic, but really on reactive power coordination, because as we just heard, we can use reactive power by stabilizing voltage, but it's not just in the low voltage grid, but it's exchanged in the upper voltage levels as well. So we have reactive power exchange up to the transmission level. And so this is a major issue. So I will give some idea of a case study where we did a specific reactive power control concept. And I will give a glance into operational perspectives that are combined with that topic. So why are we doing that? So the major driver actually in the German context again is that conventional bulk power plants are substituted by distributed generation. So this system is turned upside down. That means we need reactive power sources, which have been even today, but in the future less being provided by conventional large-scale power plants, bulk power plants, and transmission. Then we see more cabling in the system due to increase of reliability, which I showed at the beginning. We have more cables. Cables require have reactive power requirements. And so there is an additional need for inductive reactive power. Then we have seen the topic of using reactive power in lower medium voltage grids to stabilize voltage. So this means there's an additional reactive power requirement. And so this is normally more for capacitive reactive power or inductive reactive power, depending on the situation. And what we see, so I showed the phase model of the penetration. So we are now going into the situation in Germany where the objective is to operate the grids more at their limits in order to have an overall cost reduction. And so there we require congestion management, and for congestion management, of course, also reactive power is required because reactive power can congest lines, so we talk about reactive power compensation. So there are a number of drivers that are highly relevant to think about how to coordinate actually reactive power. So what is the objective? Also the objectives are manifold. One is to keep the reactive power balance. If I need somewhere reactive power, I have to produce it somewhere else. So I need to keep reactive power as well as highly discussed in this conference, balancing with active power. I also do balancing with reactive power, of course. I do voltage control, congestion management, loss reduction, and I like to avoid grid reinforcements. So there are different objectives, and all these issues are highly interactive. So I showed this slide, so I don't need to say much about that. So there is a cost reduction potential with regard to reactive power control in to stabilize voltage. This is now being done in different ways. So we can consider different control concepts. So one is, as you can see on the right-hand side, you can see the local control. So this means I only have a local measurement of voltage, and I do reactive power or I do active power control. Here we keep to reactive power in order to stabilize the system. I can also do it on the left-hand side by central control. In the control center, I have the ICT equipment, and I can run a central optimization function and apply it throughout the system. There we are going into the digitalization area, which I just showed at the beginning. We have Then in the middle, the decentral way. So beside of doing it only local or only central, we can also consider combinations of that, and we can also consider a distributed automation architecture. So what we have done here is a study through all voltage levels of a German DSO. And so, for example, applying here, just as one glimpse into the topic, we apply in the low voltage grid local reactive power control, so depending on the voltage. On the medium voltage level, we apply a combined central and local control. So that means we use also, this is given here, we use certain areas where we have, if the voltage is too high or too low, we use reactive power to stabilize the voltage. But in the area in between, reactive power is a flexibility that is available from the distributed generator, meaning that we can use it in a central control way to provide reactive power to compensate throughout the grid. Now, if we look, so we did that also with regard to high voltage. I'm not showing here. So what you see here is a measurement, actually, or no, here it's a simulation, but we validated that with measurements of active and reactive power points at the substation, and here it's a number of substations in a balance between the distribution system operator and the transmission system operator. And we see the cloud of points, and what we see here in addition are some limits. And now it is under discussion in Germany, where should those limits be, and should there be any penalties or not? So there are a number of projects, we are also involved in a number of them, to analyze this interaction between distribution and transmission. And so one first step into the idea would be, there is here, according to the NSOE demand connection code, there is a limit given, and the distribution system operator has to comply to this limit. So that means he has to control the reactive power set points according that they are not within this area, but that they are outside. So this is under discussion, how that looks like, and so on. And so we applied now a simple concept towards this case study region. So we see there is a PV installation in low voltage. So half of it, we have 30% mainly PV installation in medium voltage. And we have high voltage, where we have quite a distribution of different types of generators. So we used a methodology. So we took active power time series and of the installed systems, and based on measurement available over the former years, we applied different types of reactive power flexibilities of all the DGs with different limits. And so we are running annual simulations for that, going into a technical analysis. And we are looking then at the reactive power flexibility that is available towards at the grid supply point towards transmission. And so what we see here distributed across different voltage levels. So this is a kind of a reliability, flexibility checkup. So what we can see is that we have a very high flexibility here in the blue area, and then we have a lower reliability. And so this is depending now on the availability of photovoltaic or wind turbines. So as in the present standards, those renewable energy systems are not obliged to provide reactive power if they are not providing active power. That means they are not providing that. Of course, they can provide STATCOM functionality, but this is not under present regulation. And we see that this is especially, so the blue ones you can see again. So this is especially with hydro and biomass that is installed there. With PV and wind, we have a significant reactive power flexibility, but not at a very high reliability value. So this is an important point, because the question is, can it substitute shunt installations, for example, for compensation? So the question of the reliability requirement at the supply connection point is very important. So we applied this reactive power management concept as I already sketched with the local control combined with the central control. So it is a very simple architecture. So the objective was not to develop a very nice optimal power flow solution, but to have a very pragmatic, simple one. So we don't need any optimal power flow here. We just measure at the grid supply point, and then we distribute the reactive power requirements across all distribution units. This is working quite well in the system due to topology and distribution of plants. So considering this kind of concepts, we are applying in different projects, we are applying deployment strategy. So that means we first talk about the concept, we design it according to the requirements. Every grid operator has its own ideas and specialities. We are then going into an offline simulation, analyzing what I just showed, technical analysis, economic analysis on that. Then we are going into real-time simulation, which means we design a controller and we test if the controller operates stable and does what it should in real-time simulation, including also in the controller in the loop configuration. And finally, it goes into the field. So just giving here some impressions. So we did that for this case study as well. So we developed here the controller in this external PC. So here the central management is implemented. And then we had a simulation, a real-time simulation here with an Opal RT real-time simulator of the real medium-low voltage grid there, implementing the models for the power plants and integrating also this local reactive power from voltage characteristic. So we are applying that, and the result was that it's operating stable and does what it should. Now it's going into the field. So the grid operator is now installing this industrial computer with our controller with a graphical user interface into the field, connecting to some plants to bring it into operation. So these are different steps that are done in order to be sure that finally it operates well. And we are not so much experimenting, but we know what we do. So next to this very simple strategy, we have developed in a project, SysDL 2.0, a kind of a DMS function demonstrator. So this is, there are many ideas of what ancillary services, controllability, and so on could be done. But installed control centers are not so easily updated, so it takes normally years and from a specification to an implementation. And so we have now designed a very flexible one, which can be added to control centers. So we are already live now on two real control centers where we are able to optimize. This is now first done on reactive power. We have now a follow-up project on active power, actually. So we are getting a standard data model. This is a common information model, CIM, SIM, CGMAS, data model standard for the grids. We extract that from the control center, and then we are running our state estimation, optimal power flow calculations, including forecasting, and so we can test easily the new DMS functionalities that are relevant and under interest without going really into the control center, specifying and with very high costs for the operator, bringing some functionality in line. Of course, we have done here also from concept, offline simulation, controller in the loop simulation. Now it's in the field. A very interesting topic is here to analyze the interaction, because now we have one controller, but in reality, so I'm now in phase 2 across according to digitalization, what I just said. So if now different grid operators on different voltage levels are on the way of implementing such nice operational tools, as I just showed, they are interacting. And so we designed with a lot of effort over many years now a simulation platform, a co-simulation platform, which allows to run real-time simulations and offline simulations, where we can connect with, we are now calculating with 100,000 nodes, grids across 3 to 4 voltage levels, so we can really run a full system calculation in real time. And so we can analyze different interactions on the real grid. So we are running real-time simulations, simulating the plants, the network in detail, power flow calculations or RMS simulations, and then we apply different operational tools on different voltage levels. And this is allowing to analyze the interactions, because in reality there are interfaces. There would be in future information exchange. There might be control and set point in exchange, and this is highly important, so to be sure that the full system is operating smoothly. So we can analyze these interactions. So we use it also for controller in the loop test, as I just showed. So this reactive power management concept I just showed was analyzed in this environment. And we are also using it for testing real operational tools. So we have connected professional virtual power plant software. We have connected real DMS control center tools from leading manufacturers in Germany. We have standard interfaces with, which are available to connect this operational software in real time. So this is bringing a lot of interesting results from that. What we have also done that might be quite interesting for some of you, we have extended that now into a web service actually. So if anybody of you wants to run co-simulations, so you don't need to set up your own co-simulation platform, you can just call us. We set up the simulation. We provide a web interface with standard with some standard configuration. You can build your model, your operational tool, your software. You can do the interfacing according to the given specification. We can define the specification together. And then several of you, or TSO for example, connecting, a DISCOM connecting, a virtual power plant operator connecting. And so we can analyze via web services how it's going on real in interaction in this simulation framework. So this is highly interesting. So coming to the conclusions actually for what I've presented now. So first we need to be sure about different control concepts. So I showed a combination of local and central control concepts. And I'm convinced that finally in the system we see a combination, a hybrid configuration of different of them, because all of them have advantages and disadvantages, and we need to find the best configuration of local, distributed, and central approaches for controlling the system, not only with regard to reactive power, also with active power. This is of high importance. So I'm now more in the constellation of phase 2 and phase 3, what I showed at the beginning of the session. So ancillary services provided by distributed energy units, by renewable energies in the distribution system. This becomes a highly complex issue, and so we developed new concepts and solutions for that, and we developed a test platform to implement such algorithms and solutions that can be easily adaptable and usable and applicable. We have developed a co-simulation platform that allows to analyze these interactions in the real system. And we opened up this platform also to other users. So in some project, we are already running this web services in German context. So others are applying their market models and so on in that. And so they are very happy with that. Finally, I'd like to give a short outlook. Tomorrow morning, I have another presentation here on Panda Power. So we developed an open source tool for network planning aspects, and so the high benefit there is to run it with very large number of grids. So we can analyze a large number of smart grid technology operational concepts We look at probabilistic approaches, so we run a huge amount of load flow calculations, so not just one, not just 10, not just 100, but in many cases hundreds of millions of load flow calculations to really analyze in a robust and complex way the planning aspects of the future. And so this is an expert tool we are providing, and I will give you more insights tomorrow morning. This was also applied just to make the presentation round in this analysis. So this reactive power analysis, actually the statistical one with load flow calculations and so on, was done with this tool, so it's easy to use. So thanks a lot for your interest, and I'm looking forward for further discussions on the specific topic of reactive power coordination. Thank you.